Thank you, everyone. So the nanotechnology is turning chocolate into a diffraction grating, which makes it reflect rainbows. It's an excellent home nanotechnology project. But that's not really why I'm here. I'm here to talk about testing, and especially why is everything under-tested. So I just want to start with some questions. Who here has used PyTest? Hands? I'm so sorry. Who here has used Hypothesis? Okay, a few of you. I'm also sorry. Both of those are to some extent my fault. And for those who didn't say that you've used Hypothesis, I want to sort of explore why is that, right? You're not alone. The PSF does an annual survey, and they regularly find that like 4, sometimes 5% of respondents use Hypothesis, and about 50% use PyTest. So in this room, we are much more excited about testing tools than most people in the Python community. Maybe there's a selection effect of some sort. But when I say, why don't we test things enough? Why don't we use these advanced tools? Why don't we use stuff? I really don't mean formal verification. People like the idea, especially in academia, of being able to prove things about your code. And any decade now, it might be ready for use in industry or practical projects, but it's really not yet. So what I mean is techniques which I think are just as productive, that take no more time, not any particular new skills to learn, but can give you more leverage, that can have the computer do more of the work for you compared to writing manual unit tests. And to give you a concrete idea of what that looks like, I thought I would write a test for a sorting function. And so if you use Hypothesis, this is a complete executable example of using Hypothesis. We say given ... so it will infer what to generate from the type annotations. We have a test where the list ls is a mixture of ints and floats. We get the output by sorting the input list, and then we assert that we have the same number of each element in the input and the output, and we assert that for each pair of elements, the earlier one is equal to or less than the later one. Does that make sense? Cool. The usual objection is like, okay, Zach, this is cool, but sorting is a sort of toy example, and hey, it's not even in the standard library, it's a built-in. Do we really need to test sorting? How do I know what to test in my code? But before that, what happens when I run this test? I'd like to hear audience suggestions. What do you think happens when I run this test?
Hypothesis generates a bunch of random test numbers.
It does. And then what happens? It fails. Why does it fail? It fails because not a number is not less than or equal to any other number. And so Hypothesis will generate you a list containing 0 and not a number, and then the test will fail. You're like, okay, I didn't really care about that. Thanks, Hypothesis. Such is life. And so there is this broad range of testing technologies we can use. Who's used linters like Flake8? A lot of people. That one's also partly my fault, sorry. Linters are very cheap, they offer very fast feedback, and I think they're a fantastic tool to use whenever the false alarm rate is low. The typical problem with linters is that they start telling you about a whole bunch of things that don't actually matter to your project, and they get annoying and people turn them off. But I think if you run linters where they only alert you about things you actually care about, they're a fantastic tool, and they should be used more there. Then there's randomized testing. I still have these classed as cheap, and hopefully if you're in this talk, you're at least interested in learning more about them. Unit tests, I'm kind of down on traditional unit tests. There's a place for some of them, but I think they've become the dominant way of testing in many places because they're the sort of easy go-to, you don't have to think too hard about it. But I would essentially only try to use them to fill gaps in a different testing strategy. To use Hypothesis for things where I can say some sort of general invariant, and then unit test to cover the gaps. Sometimes people who want to write correct code in Firefox, for example, just invent an entire new programming stack. And who here has heard memes about rewrite it in Rust? Only one person. Wow. Wow, I guess it is a Python conference. I think inventing a whole new stack is pretty cool, and whenever you can get away with it, which might be like once or twice in your career, go for it, have fun. And then when people talk about full program verification, you're basically talking about inventing a new stack because you get to do like 30 years of research before it's actually ready for production. But my argument is not that we're making a key mistake here. I would love people to use Hypothesis more. But I think that people who are proponents of better testing tools actually need to build tools that offer people a more attractive trade-off. It's an easy pitch if you can say, this will save you more time as well as finding more bugs. And then the barrier tends to be people need to learn how to use it or need to hear that it exists. And so I think about this when I'm working on a hypothesis as having essentially 3 goals. I think the library is already pretty good. But for it to have the most impact that I want, to help people write robust code all across the Python community, we need to work out how to increase adoption, just the number of people who use it at all. But when I see the survey and it's like people say they use it, I don't know whether they mean they write 1 test a year or whether they consider it an indispensable daily tool. It's just not at all clear. And so I also want to find out, how can we increase the intensity of use? How can we make it useful more often for people who are already using it? And then the final part of this, I think open source libraries often end up focusing on power users because the developers and the maintainers of open source libraries tend to be power users of that library. They tend to know the domain deeply. They tend to think about it a lot. That's probably why they wrote the library in the first place. But even though I think it's usually overemphasized, it is still an important thing to make this tool as flexible and as powerful as we can without compromising the experience for new users or making it harder to learn. So, like, maybe Hypothesis just should only be used by 5% of Pythonistas? Like, no, I think most of you should be using it. And so we've got these 3 goals: adoption, intensity, and power. And I'm sorry if I sort of misrepresented a little, but I'm not going to give a talk about the cost-benefit trade-off of, how do you balance these things, but rather, how do we get a better trade-off? What kind of features do I engineer into the library that try to make it more powerful or easier to adopt? And that means it's basically a talk about the squishy humans. Programmers are not famously excited about the squishy human feelings, but they really matter. Right? When we talk about the Python community, it's a community of people. And it's the people who I'm building this library for. I work on AI day to day. It turns out that AI models use my libraries as well, but I'm not building them for the AI systems, I'm building them for the humans. So where does that leave us? It leaves us with me having spent the last 5 or maybe 8 years. Yeah, this is a blank slide in the middle, actually. We will get on to more soon. Yeah, see, that looks like a technical problem, but it's actually a social trick to make you pay attention to what I'm saying. I'm so sorry. And so I've spent this time thinking about, how do I build a technology? How do I design a library to accomplish this social goal of helping more people use the tool, making it easier to learn the tool, and increasing the power that you can get out of the tool? And that means I have been working on technical solutions to social problems. This is an idea that gets a bad rap sometimes, when people are like, I will simply build a website that will do ... But I think actually most of the world seriously underestimates the power that we have as technologists to reshape the possibilities that other people are choosing between and to give them better options that they can choose. And so a lot of what I'm doing is, in fact, trying to come up with features, library features, sometimes language features, that I think will give people the power to make better choices or to choose between better alternatives. And so I'm going to dive a little into specific problems we've faced in Hypothesis. Again, Hypothesis is this library for writing better unit tests where you say, for anything in this kind of category, this test should pass. We saw that with the sorting example. So problem number 1 is that users didn't read the documentation. Who here has read the documentation for all the libraries they use? Yeah, we've got no liars in the room, that's nice. So what do you do when people just don't read the documentation? Well, you do have one opportunity to make sure someone reads something, and that's your exception message. Because people are just going to try something, and then it's not going to work, but you probably get 1 line of text where they're going to see value error, ... And so I think it's something like 1/3 of all the code in Hypothesis exists in the service of giving more helpful error messages. So that whenever people do something that indicates a misunderstanding that I've seen on Stack Overflow or on the issue tracker or talk to someone about at a conference, Hypothesis will usually give them an exception with a message that tries to clearly explain what just happened, what I think they were doing, and what I suggest they do instead. And so the library itself becomes a tool for teaching people how to use the library. We also have documentation, but do people read it? Unclear. And the other thing that we do here, it's not just error messages, we try to have a design where once you understand a few basic concepts or design principles, the whole library is really about composing these simple primitives in ways that you can learn once and then apply many times. So if you're wondering, how do I generate dictionaries of things, you can think, well, it's probably about the same way as I generate lists of things. I honestly observe this principle more in the breach. Hypothesis goes to great lengths to present a surface veneer of everything being nice and not magical and being simple and composable, and under the hood, we do crimes. You probably think, for example, Python is an interpreted language, but it turns out you can just get the source code of a function at runtime, and then get the AST, and then modify the AST, and then compile that back to a code object, and then reassign it to a function. There's fun stuff like that. It's a power that I promise we use for good, not evil. And then the second big one, there's a lot of academic research on property-based testing, which tends to focus on how do you generate the right kind of input data to your test. But when you actually do user studies, you find that people are pretty comfortable working out what they want their test to have as input data. Spoiler, it's usually just integers. Sometimes it's lists of integers, but usually it's just integers, sometimes strings. And so the real question that people get stuck on, especially when they're new, is that the library sounds cool, but they're not sure how to apply it to their code. And I just want to see a show of hands. Can everyone willing to put their hand up, put their hand up? Okay, great, that's a lot of you. Put your hand down if you already use Hypothesis regularly. Okay, put your hand down if you are confident that after this talk you could go use Hypothesis. And for those who are left, I'm guessing a bunch of it is you're just like, well, it sounds cool, but how do I do that on my code? Yeah, you are not alone. And so one thing that I do is I give talks like this, where I just try to make it friendly and approachable. I try to make the library itself friendly and approachable. I write the documentation that no one ever reads. But the other solution that I've pulled out is what I call the Ghostwriter. This was inspired after a trip to PyCon a few years ago, where I was like, fine, if you don't know how to apply Hypothesis to your code, I will teach Hypothesis how to apply Hypothesis to your code. So this predates all the modern language model era. It uses good old-fashioned AI techniques like regular expressions and type inference and dictionaries and if statements. But the net result is that you can point the CLI command hypothesis write at your code. You can use the help to see what's going on, and it will read your code and it will say like, you have a function called encode and a function called decode. I bet that if I encode something and then I decode it, I should get the same thing back. Or I have a function called A to B and a function called B to A. I bet those should round trip as well. There are a bunch of special cases, but collectively they cover a fair chunk of valuable tests to write first, because those simple round trips, save and then load, serialize, then deserialize. These tend to cross many layers of abstraction. Almost all code bases have them. Right? If your code never saves output and never reads input, it's probably going to be pretty easy to test because I've got a great optimization available. You just do less work. And so the Ghostwriter does not actually aim to produce complete finished tests that are ready to run. When we're lucky, if you have type annotations, it will do that. But the real goal is to give you a starting point, to get you over the empty file in a text editor problem and have something concrete to work on next, because you will get tests, you can run the tests, and they will fail with an error that says, you need to tell me what this argument really is, for example. Another problem that people complain about is flaky tests, which are just awful. Who here has flaky tests? Who here likes flaky tests? Yeah. So what do we do about flaky tests? Hypothesis can be run in a deterministic mode, but I don't usually recommend it. So we have a couple of other features designed to eradicate flakiness while still getting the power of random exploration. The first is what we call the database. Every time Hypothesis finds a failing example, it will record the underlying choices that it made to generate that failing example, And then in future runs, it will replay those failures before it starts fresh random generation. And that means that if you happen to stumble over an unlikely failure and you run your test again, you can be confident that if it doesn't fail for the same reason again, it's because you actually fixed the bug. Without that, you would be stuck running the test repeatedly and sort of guessing about whether the statistics were good enough. The second is that we have a bunch of features deliberately to enable replay. You can write, for example, @example and a particular input that you want hypothesis to always try. And so this is another way that you can mix random exploration and then explicit recording or documentation of, this is an input which failed before, I always want to make sure this one is tried again in the future. And then I mentioned the deterministic mode. If you're truly paranoid, you can just get hypothesis to do exactly the same thing every time. And that means that you rule out the possibility of finding those rare bugs in subsequent runs. And sometimes that's a trade-off people prefer. Sometimes your goal with testing is to go find bugs, and other times your goal is just to check whether this proposed pull request introduces new problems. And those are both legitimate goals of testing. A converse problem, though, is that some bugs are really hard to find. Has anyone here known about a bug in their code but been unable to find it for more than 6 months? Yeah. My personal record is about 2.5 years and 7 people. The bug was on PyBay, on 32-bit Windows, if you overflow the unsigned integer pointer type in a standard library array, it wraps instead of raising overflow error. This was buried inside an internal hypothesis data structure, so it was very difficult to trigger reliably. It was a very good day when I got a repro that was 2 lines of code and handed it to someone else. But there are a couple of things we can do to find very rare bugs without requiring you as the user to do anything differently. You write the test once, and then we can attack that with a variety of different techniques. So the first is that hypothesis has a bunch of heuristics built into it. That you could do a naive thing with a random number generator where you say, give me integers between 1 and 1 billion, and it just randomly generates integers. But probably 0 and 1 and 1 billion and 999,999,999 are more interesting than most of the other values. You might also check powers of 2 more often. You might check prime numbers more often. There's a bunch of tricks you can do. And so hypothesis builds in a lot of these heuristics so that you don't have to think about which edge cases should I test. You can just trust that we have built those in. And we have a few tricks, like we will read the source code of the file that we're testing and find all of the constants in the source code and try generating those. So if you have branches, for example, compare this to that string, there's a good chance that that will just happen to come up. The second thing we can do is fuzzing. Who here has done fuzzing stuff before? Small number of people? Fuzzing is basically an evolutionary search process. The idea is that where hypothesis by default will just sort of keep throwing stuff at your code and see if it fails. With fuzzing, we actually do that, but under coverage measurement. So we can actually watch, in some sense, what happened, and we can therefore notice if some input that we tried did something different that we hadn't seen before. And if you can tell when you've seen something new, and you can try variations on things that you've done, this allows you to sort of slowly explore and ratchet your way through the space of possible behaviors of the program. And in the best case, that turns an exponential search into a relatively cheap polynomial search. And the last trick here, which is just black magic, is SMT solvers. Has anyone here heard of SMT solvers? A few people again? Okay. SMT is a generalization of the Boolean 3-sat problem, which is sort of the classic NP-complete problem, where the goal is to find an assignment of values to a set of variables and equations such that all of the equations are true. Basically, it's a way of getting computers to reason about the code very rigorously. And about 20 years ago now, Microsoft Research started using these for software testing. So you can actually have a system which explores the code and rigorously tracks everything the code could do and will keep trying unique behaviors until it's seen all of them. And so if you have a test which only fails if the sum of 4 things is exactly a 32-digit number, a SAT solver will solve it that quickly. There are other things where it just can't help at all. And that's why having this mixture of techniques, I think, is really valuable, because you can write the test once, and then you can run your tests with every different backend and just see if each of them shake out different bugs. Another problem people have: why did that test just fail? Is it a bug in my code, or is it a bug in my test, or is it a bug in my infrastructure? Did the CI runner just flake? Did my code just flake? There are a couple of things we do here. One is that hypothesis doesn't just give you failing inputs, it shrinks them to give you minimal failing examples. Anyone here used Stack Overflow? Yeah, Stack Overflow loves minimal reproducing examples, and so does hypothesis. They're just genuinely much easier to reason about. And you can also tell by looking at them sometimes that every part of this big object is the simplest thing except for that part of it, which means that that part of it must be part of the cause of the bug, because if it wasn't necessary, hypothesis would have shrunk that away as well. The second trick that we have is what's sometimes called fault localization. And so this again is, once we find a bug, we can start running under coverage, and we can tell you that some lines of code will always run by failing examples and never run by passing examples. And that's not always the solution, but it's often a pretty valuable clue as to what's happening. There are also a huge pile of heuristics in there to say things like, if the line that is always run by failures and never by passing test cases is raise blah, 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 that one's not interesting. Don't bother pointing that out. And then the last thing we can do is actually annotate those minimal examples. So if you're testing a calculator, for example, you have a number A, an operator, a number B, and you'll pretty quickly have hypothesis tell you that 0 divided by 0 gives you 0 division error. And you're like, okay, great, that's a lot of zeros. It's been a while since I did arithmetic. Which of those zeros is the problem again? But hypothesis now will actually shrink all the way down and then try varying each of those arguments independently to see if the test still fails. And so now hypothesis will tell you 0 or anything else divided by 0 gives you 0 division error. And that can make it a little easier when it's relevant to tell what's going on. Why is this so slow? Am I even talking about testing, or is this just like computers might have been a mistake day? We can just make it fast. One option is to work out how we speed up. We have done a lot of profiling with the library. It's pretty fast. The second thing we do is observability. Hypothesis has an option to dump a lot of detail about what each test case did, so that you can analyze that with pandas, with dataset, with your tooling of choice, and understand, are there correlations between input size and latency, for example. And then the final thing here is that sometimes we do some interesting tricks to make things faster than they otherwise should be. For example, you can filter things, and hypothesis will sometimes just recompile the whole generator at runtime so the filter is always satisfied. If you say, for example, give me integers, dot filter, lambda x, 1 less than x less than 10, approximately 0% of the integers are between 1 and 10. But because we can get the syntax tree of that function, we can work out what bounds it's expressing and then recompile the underlying generator to always satisfy them. It's kind of cursed, but it's a cool trick. So, why is everything under-tested? I tend to think it's because we need to work on increasing adoption, intensity, and power. As developers of these tools, if people aren't using them, that's to some extent our problem. And I've hopefully pitched you on, the tools are cool. The tools are worth using and relatively easy to pick up. So, what would happen if we made some testing libraries and no one came? And honestly, I don't really have much of a leg to stand on here. I am a busy guy. It is not my full-time job to work on open source. But I've done a bunch of it anyway for some reason. And so I want to invite us to build our libraries and to think about the tools that we're building and the applications that we build on top of them for people who don't test yet or who don't use them yet, not just for the people who are already our users. So, thank you for listening. I would be delighted to take questions or even comments from the audience. Just one question, I think.
Hi, thanks for the talk. I haven't used hypothesis before, so maybe this is a basic question, but can hypothesis test basically, or do these permutations for like which platform you're on and how you're installing? For example, like Linux on installing with PyPI versus like Windows with, Poetry or something.
Yeah, so Hypothesis is a cross-platform Python library. It's pure Python, so it's easy to install anywhere you can use Python. And if you're testing a file system thing, you might see variation. But fundamentally, Hypothesis helps you write better test functions, and anywhere you can run a Python function, you should be able to run a Hypothesis.
Oh, I guess I was talking about like the distribution stage.
It's on PyPI, it's in a bunch of Linux package managers.
Yeah,
it's
but testing the permutations of what a user's setup might be.
That is a question for your test function, rather than for Hypothesis. So if you can write a test function that does that, you can then provide arguments to that using Hypothesis. All right, we had one question down here, and then I think we'll be at time.
Yeah, so besides the barriers to using the software, like why don't people test in the first place?
Why do people test in the first place?
No, why don't?
Why don't? I think there are a bunch of reasons. For some people, it's just that they never really learned to test, or people never explained to them why it might be worth doing. Sometimes I don't test my code because I'm more interested in exploring whether an idea could be possible than establishing whether it does work. Some people describe testing as a tool for collaboration, especially over time. So tests help you make sure that the computer can check whether your subsequent changes break your earlier work. And I think in that kind of thing, it can be very valuable. Unit tests, I think, don't help you that much establish whether the code that you just wrote is correct, because it's pretty unlikely that you will think of an edge case just because you tabbed over to a file reading test_thing. But Hypothesis can think of those edge cases for you, and I think that makes it a lot more powerful for finding edge cases, finding bugs that you wouldn't have thought of. So those can all be reasons to test, but people don't do it for all sorts of reasons. All right, we are at time now, but I'm happy to take more questions and discussion just outside. Thank you all so much.